All right, so good afternoon. How's everybody doing today? All right, so we are out of Birmingham, Alabama. There is something that does come out of Alabama other than Alabama football, so just to start you off there. I'm assuming that most everyone here came here on an aircraft. I think that was asked earlier today. And one of the things that you probably don't think about is when you get on an airplane is that it just works, right? You get on there, you're moving through the air at 500 or 600 miles an hour in a very thin aluminum tube, and you don't think about the physics of what's required to do that. And that's really important. I've spent the last 20 years of my career in aviation, both as a pilot and as an operator, and I've got to tell you, when I go to use something in an airplane, if I push that button, it needs to work, right? So what we want to talk to you about today is something that we believe is going to be very useful. Where's my clicker? There it is. So I like to start off this with a good story, right? So about 7 or 8 years ago, myself and a colleague, my friend Jeff here, we were flying from Singapore to Melbourne, Australia. And we were climbing out of 35,000 feet in a business jet, not one of you guys' products. I just sat down, turned the autopilot on. We were getting in the cruise. The flight attendant came up and brought me my plate of risotto, and I was just getting ready to start eating. So as soon as I take this plate of risotto and shoveling it in my mouth, maybe 2 seconds later, we get this alarm. It goes ding, and I'm like, oh, what's that? It's like, he goes, the right generator failed. I'm like, oh, that's a problem. Get the checklist out. Let's run it. So we start running through the checklist, and maybe like 2 or 3 seconds later, ding, and then more dings, and then screens start going off, and it's like, oh, wait a minute. Now the left generator's failed. So now we've gone from a minor troubleshooting checklist procedure that we train for all the time to, okay, now we're going to have to do some stuff to make some stuff happen and think about how that stuff is going to affect our flight. And the most important thing for us is to get another generator back online, because that battery, maybe, they tell you 30 minutes, maybe 45 minutes if you hold your nose just right and you pull all the right circuit breakers and things work out. So we went through the process. We were able to get both generators back online. The reason is really not that important, but it got us to thinking once we got on the ground. We're like, you know, we've got 2 perfectly functioning motors, airplane's still flying, but unfortunately, we don't have a way to generate any electrical power. That's a problem. So we started thinking about what would be some alternative ways to generate power. So, of course, this conversation happened in the bar, because if you know Jeff and I, you'll know that every brilliant idea we've ever had came up with in a bar. But we came up with the idea of thermoelectrics. And thermoelectrics have been used for a very, very long time. They've been used in the space program. They're used for Voyager 1 and Voyager 2 space probes that have been running for 40 years. This stuff is the material science is very well trodden. They understand the material characteristics. And we thought, well, with the amount of waste heat that we generate in an airplane, and we have a very incredible heat sink in the amount of cold air we have outside, we can create a really serious temperature delta to make this work. So let me tell you a little bit more about thermoelectrics. So how do thermoelectrics work? So I have this awesome slide right here that you guys can look at, right? And it shows you that you get a hot side and a cold side, and the temperature differential creates electricity, right? And that makes sense to most people, but I'm going to show you exactly how this works. So I've got just a heat gun. I want to introduce a heat source to this. So it's just basically 2 heat sinks with a bit of thermoelectric material smashed in between it. And as the temperature differential increases, it generates electricity. It's that simple. It just works. Now, I can remove this heat source, like so. The electricity will keep generating, because as long as there's a temperature differential between the hot side and the cold side, we still have electrical power. So I'm going to set this back down right here. So that's half the equation, right? So because that's fairly bulky, you can put it in an airplane, but you've got really big heat sinks, and these modules typically are planar like this, right? And they have to be held in compression because no surface is perfectly smooth, and you have to have thermal grease, and you have to have all these heat interface losses. So the challenge for us was to take something like this and make it into something useful that would be lightweight and rugged. So what we did was we looked at creating a thermoelectric tube. So instead of something that was planar, where you had a hot side and a cold side, now you have a tube shape. So now your hot side is whatever runs through the interior of the tube, and your cold side is whatever is on the outside. Your heat sinks are now integrated into the module, and now it's, instead of being a fairly flimsy ceramic type material, this is now a very, very rugged, very well-built system that we can now integrate into a heat exchanger. So each one of these modules can be threaded together to create a pipe. And each one of these modules at a 200-degree temperature delta between the hot side or the inside and the outside can produce a 1 watt at optimum power output. It can produce about 2.5 watts. So if you take all those and you put them together in series, now you can create a tube and shell type heat exchanger. So anything that goes through the interior of the tubes, that is your hot side. Everything that goes through the outside of the tubes, that's your cold side. And if you put those tubes together in series and series electrically and thermally in parallel, now you can generate a ton of electrical power. What's the advantage of having a thermoelectric heat exchanger? Well, in an airplane, it can reduce the size or the number of batteries. Some airplanes have 1 battery, some airplanes have 2 or 3. Why that matters? Well, I mean, battery's dead weight when you're not using it. So during start you use it, in an emergency you use it. Every other time it's really not doing you any good. It's just extra weight. We've got an opportunity for a huge temperature delta. Well, solid state construction means there's no moving parts. It'll last a very, very long time. The radioisotope thermoelectric generators that have been powering the Mars rovers, as well as the Voyager 1 and Voyager 2 space probes, those have been running for 40 years without fail. So it's a very proven technology. The other thing is that it's isolated from the engine operations. Therefore, it doesn't take any additional fuel to power them, except for the small additional weight gain that you'd have. And it doesn't have any drag on the performance of the thrust of the engine. So what would one of these look like? So again, this is a rendering of how it looks on a component level. So we start out with the heat exchanger itself. You can see the individual tubes, and as everything dissolves, we have the individual module. Now, that module took quite a bit of design work because bismuth telluride is a very reactive material. The tellurium tends to react with everything. So for us, the high hurdle was finding materials to make the heat sink that wouldn't react with tellurium, so that we could have a very long-lasting device. So again, I wanted to show you how the hot side and cold side works. So you have cold air coming through the top, and then the tubes would be in the middle. And then you have hot air coming through the tubes. And we've been able, through the simulations that we've done through CFD, we've been able to mirror the performance of a pre-cooler that we've taken from another airplane. So here's what the output looks like. Each one of these tubes, if you had a 9-inch long tube, which is basically 17 of the individual couples, that would produce at a 200-degree temperature difference between the hot side and the cold side, that would produce about 20 watts. And here you have a power curve, so right at about, and that's a matched load of 20 watts. At optimum conditions of about 340 degrees as a temperature delta, that same tube would be able to create 58.1 watts. So again, the model that we produce has about 32 of those put together. 32 of those tubes put together. So that just small unit that weighs about 16 pounds can produce about 1.5 kilowatts, give or take. So here's an example of a typical bleed air system. I know you guys may not know how this works, but the most important thing you need to understand about an aircraft and an aircraft engine is how they heat, cool, and pressurize that airplane is they take compressor bleed air, which gets pretty hot, and they run it through a heat exchanger like a radiator. And that's a pre-cooler, and that's where we're integrating our technology. Air goes in at 350 degrees, they blow cold air across it, cooler air comes out the other side. Right there is where our opportunity is to generate additional electricity. So what are the industry impacts? Well, it's very difficult to get a sustainability product into an airplane. Like it's not, an airplane has a lot of different compromises that you have to make it perform. So it's not an easy task. So one of the things that we think that we can do is if you get a 10 kilowatt thermoelectric generator, about every kilowatt that you generate from an engine-driven generator has about a 0.02 to 0.06% per watt effect on the fuel flow. So what does that mean to me? Well, if you burn 1,000 gallons in an hour, I can save you, if I can get a 10 kilowatt thermoelectric generator on your airplane, I can save you 6 gallons of fuel. 6 gallons of fuel per hour. So 6 gallons of fuel per hour, 1,000 hours a year, that's 6,000 gallons times however much fuel costs today, maybe $1.46 today, maybe $5 or $10 a few years ago. The additional thing that we have is that we can improve the safety and reliability. So if we set the Wayback Machine to where when Jeff and I were in our situation and that had happened, if we'd still had a thermoelectric generator that we could use as a backup system, we would have still had power and we could have still flown on to our destination, even if we hadn't been able to get a generator back online. Increased engine performance is another big thing. So every bit of energy that you use to do anything but produce thrust from an aircraft engine is energy that's not propelling you forward. And I bet our friend from Pratt & Whitney would love to have all of the power that engine produced dedicated to just producing thrust. But unfortunately, we have to do things like keep people alive and play the movies and keep the lights on. So we have to do that. But we can offset some of that by taking advantage of this type of technology. And then again, the last thing is that reduced fuel flows equals reduced carbon emissions. So what does that mean overall? So we can save the commercial airlines if we were able to, if I was king and I could snap my fingers tomorrow and I could integrate this technology into every single commercial aircraft out there. There are about 21,000 of them right now. We could save them, start saving them tomorrow, $150 million per year, which is significant to an industry that operates on 2% margins. The commercial airline industry uses about 16,820,700,000 gallons of fuel in a year. So just a 0.5% reduction in that fuel would equal 81 million gallons saved just for US domestic commercial carriers. And then again, the industry has targeted 2 to 3% reductions in carbon emissions over the next 20 years. And what we have can make a big dent in moving that process forward. So just a little supporting info. If we were to win the Gulfstream Navigator Award or the Orcel Award, we would use that money to move ourselves from the current technical readiness level that we are, which is like technical readiness level 3. So there are 9 of these things before I can put my device in your aircraft that you're not going to think about. So it has to be safe. So we'd like to get to technical readiness level 5 or 6. That requires prototype testing in the relevant environment and a scale prototype. So there's the team. That's myself and Mark Froelich, our CEO, and Jeff Lane there. And our key partners were Heisey Technologies. They've really done a lot of the work on helping us develop the thermoelectric modules and creating the design. Dr. Alex Cush and Mr. Fred Levitt. So that's it, Alteg Systems, DC power from waste heat. You guys have any questions?
As usual.
My man Brad's up in the front.
Is there any breakdown over time for the material inside the heat exchanger and what happens to it?
Okay, so typically what happens with these materials is that you will get a degradation over long durations of time. Now, that degradation is mitigated as long as you keep it within the temperature ranges. So this material is happiest around 350 degrees Celsius or lower. So as long as you stay within that range, you should have very little to no degradation. And what you do would be, we're talking operational life of maybe 20,000, 30,000 hours before you have any real serious degradation.
Over here.
Yeah, you talked about using this technology in aircraft industry and aerospace. Are you thinking about it, using it this in future in maybe automotive industry?
Well, that's probably where a lot of the work is being done in thermoelectrics in the automotive industry and vehicle exhaust. So I believe BMW, GM, Ford all have DOE-funded projects that are doing that. It's a very different equation because if you think about engine exhaust, it's far higher than those temperatures. I mean, that's the low side. So it requires a different material. In addition to having that different material, those materials are very expensive. So some of the generators that have been produced for the automotive industry are very, very expensive, maybe $4,000 or $5,000, and for cost of materials, which is very, very high for a production automobile. Hope that answers your question.
Over to the left.
Hey, my name is Greg Gaffey. I have a quick question, actually kind of a two-part question.
Bring it on.
What is the actual efficiency you're getting from the tube cell itself, just from the 350-degree delta?
Okay, so at the 350-degree delta point, typically what we have is about a 7 to 10% conversion if everything is working the way it's supposed to. 10 on the ideal, 7% as a low point.
And I guess the second part was, have you looked at anything like a metal foam to increase the efficiency instead of just the pure tube?
Yes, so the geometry of the interior of the tube can be changed based on specification. There's a certain temperature. The bleed air temperature can't be 0.
Yeah.
It needs to be hot because we use it for anti-icing and de-ice. We also use it for a couple of other different things. So it needs to be typically it's right around 180 degrees. So we need to cover that spread as well as to be able to produce electricity. So that's why there's a variance to the geometry of the interior of the tube.
Yeah. Okay.
Okay?
Thanks.
And another question there, Chuck.
Yeah, so I've learned that weight is incredibly important in aircraft.
You're right.
So can you say what is the net delta in weight to add this technology to the aircraft?
So when we started our modeling for this, what we did was we took a pre-cooler from a small jet, and we basically took the guts out of it and turned it into a shell and tube type heat exchanger that we showed earlier in the slide presentation. When all was said and done, the expected weight of that was about, the actual weight of the unit itself was about 12 pounds, and the end weight that we have projected is about 16 to 18 pounds.
Did you have another demo that you were going to show?
Oh, yeah, we did. So this is a very small scale demonstration of how thermoelectric power can work. This, if you'll allow me, is a larger scale demonstration of how thermoelectrics can work. So here is an aircraft instrument. This is a E80i, and it's basically being powered by 2 or 3 thermoelectric generators, thermoelectric modules, on a hot plate. And this is a very simple instrument. It only takes a few watts to run, but it's very, very simple. And you can show that there's nothing more than just the heat and ambient air being drawn through a fan that's powering this. It's very simple. It just works. Question?
Have you used this in other applications like dry suits for diving? Self-sustaining?
There's been some work done. Yes, there's been some work done with that, with flexible materials in thermoelectrics, but it's a very different field than what we were looking at. The field of thermoelectrics is kind of littered with companies that have tried to integrate this and have had a solution for a problem that nobody had. And so that's kind of what we're trying to avoid. We saw a problem, and we saw that the industry is demanding more electrical power from aircraft because more and more systems are being powered by electricity. I mean, if you look at the Boeing 787, that airplane is almost entirely electric. Everything from the landing gear to the pneumatic system, everything's electric. So they found that if you can produce the power, the trade-off for the fuel consumption is worth it. So for us, if we can produce power without using any fuel, using something that was completely wasted, that's the direction we'd like to go. I'm going to get back on the stage.
Question over on the left.
Yeah, so I have 2 small questions. One of them is, I couldn't tell from your presentation whether existing craft can be retrofitted with this? And if that's true, have you got a cost per unit or some way of demonstrating what the cost is of making this happen with existing craft? And the second question is about monitoring. Is there a device that goes with this that indicates its efficiency level and when it needs to be replaced, and basically how it's doing over time?
Okay. So retrofitting something like this could be done fairly simply, just by what we would need to have is we would need to know what the geometry is of your current pre-cooler, and then we could decide what type of integration we could do and what would the potential power output that would be. And if that was something that would work for that particular manufacturer, then that's what we would use. Your second question was about unit cost, right? When we talk about unit cost, what we can, because we're a pre-revenue company, we have to think about what our material costs are, and then what our cost of production is, and then whatever the markup is there. So, and that's a difficult thing to nail down because the scale, like something for a very large transportation category aircraft is going to be a lot larger than for a smaller business jet per se. So I don't have a very good answer for you as far as a general cost per unit. But I think as we get a little bit further along, I could be able to give you that.
From a certification standpoint, are you intending initially for this to be a supplemental generation system and then over time get certified to replace the other systems?
That's a great question. So we have to think about like what's possible right now and then what's possible in the future. So, the interesting thing about thermoelectrics is, theoretically, the efficiency can be very, very tremendously high, far exceeding solar by a lot. But what's achievable right now is offsetting some of the power from the engine-driven generator. So if I can save 5 or 10 kilowatts an hour from that engine-driven generator, that is real cost savings. That's going to be passed on to an operator.
That looks like that, Bash. Great job.
Thank you.
Thank you.